welcome to another video, and in this video we are on a quest to build a strong planetary gearbox for my robotic actuators that will be fitted onto the powered armoured exoskeleton project. Now, a little recap on the work so far on the actuators, at least for the gearbox side of it. The actuators in question are quasi-direct drive actuators that basically have a brushless motor at the back, and then at the front they have a planetary gearbox, which then attaches to the exoskeleton. Now, because milling parts out of steel can be quite expensive and actually quite difficult to find someone to do it, I have in the past experimented with having gears laser cut out of steel instead of having them milled. Now, this did work quite well, but it does actually push up the cost of the actuators by quite a lot, and more to the point in my opinion is you end up having problems just getting any of this work done because it's always going to be little small pieces that aren't worth enough to whichever company you're essentially trying to outsource this work to. So I want to be able to build all of these parts myself, which unfortunately does mean I don't have a laser cutter to use. And on the 3-axis CNC that I've got, trying to mill any parts out of steel would take far too long. So instead, in this video, we're going to be trying to make a carbon composite gearbox. However, while I do want to experiment in the future with a fully 3D printed gearbox, one of my issues is with 3D printing the gears is you don't necessarily get a hard running surface from the 3D printer. So what I'm going to be trying today is basically material that I ended up using on the old prototype, and that is carbon fibre with acrylic plastic sandwiched in the middle. I originally used this on the old prototype for the pelvis piece. I basically needed a big, really strong piece of material that I could machine and put holes in everything, but I didn't want to do that out of solid carbon fibre because I knew it'd be astronomically expensive and I might make a mistake, meaning it'd all be for nothing. So I was thinking of what I could do, and at first I thought, well, I could put foam in between it like they do on aircraft parts and on drones, but I don't need it to be lightweight and it's only going to be less strong, so how about just sandwich plastic in between it? Obviously I won't be the first person to do this, but I was actually quite surprised at how strong it really was. The brittle hardness of the acrylic made it incredibly stiff, while the carbon fibre's strength and small degree of flexibility made it incredibly strong, providing it was bonded together with a decent bonding agent. And one of the biggest pluses to me was this machined very well on the CNC. All of the holes came out perfectly. Acrylic always machines really well, and carbon fibre does as well, providing you keep the dust down. So I bought a cured sheet of 2mm carbon fibre and then some 5mm black acrylic, which will now glue together and then get it ready for CNC machining. That way I'll be able to cut out all of the gears, the ring gear, part of the hub assembly, and then I'll just be 3D printing some of the other parts. They'll be at least strong enough for the test. At which point we're then going to try and test this to destruction and see when it fails. Hopefully we'll get more torque out of it than a Honda.
And here is the 5mm acrylic. I'm just going to sand this top surface up and get it ready to bond the sheet of carbon fibre onto it. With that roughed up on both sides, we'll get the sheet bonded on. I found this Sodal Fix-All to be the best. It tacks on very well, but crucially when it's cured, it still remains quite rubbery but sticky at the same time. One thing that doesn't work with this is if you use epoxy resin, it does basically just crack off the acrylic and the carbon fibres, so you do need to use something semi-flexible. Once I've spread it out nice and evenly, I'll get the piece of carbon fibre on and then do the same on the other side and then weigh it all down so it can cure overnight. And of course, always forget to check the angle you're filming at so you're barely getting the pieces in frame. Now it's cured and then cut out, we'll get it ready for CNC machining. And yes, just ignore the fact that I do need a new workbed. However, I've been ignoring that for quite a while. Now, I've seen quite a few people put their carbon fibre in a nice little tray and then fill the tray up with water to keep the dust down. However, I have found that ATF oil works excellently instead. Just layer it on over the top and all the dust just gets trapped into this nice paste that you can clean off after. Now, because I was cutting with quite a small bit, a 2.5mm bit, I did go pretty slowly. But as you can see, it did come out pretty well. I think though, actually in future, if I go faster, I'll get a little bit of a better finish on the plastic. But this is all the material I had, so I didn't really want to break a bit and then have to start again. I haven't shown this design in CAD just because it is the same design that's been in different videos, just made out of different materials. But we have all of the bits getting built up. We've got the bearings in the planetary gears, as well as the hub drive piece, and then some 3D printed pieces to make up the planetary gear carrier. All pinned together with 4mm steel rods, hence why there is some grinding marks on that top bit. And then we've got the front cover with bearing, as well as a couple of shims and the back plate. So we'll just quickly get it built together. We've got the planetary gears in the carrier slotted into the ring gear, with the hub drive fitted with some bolts that hopefully will grip a socket. And then the front plate, rotate it over, put the ring gear on, put the shim on, and then put the back plate on. And then I've just made a slot in the sun gear so I can jam something in it to lock it up into a vise.
It is now time to get this locked up in a vise and ideally tested to destruction. However, the lighting in my garage is absolutely terrible, so I will be doing some sacrificing of this kitchen table.
And it is at this point where I'm going to ask you to like, subscribe for my dedication in trying to make this video as good as possible. Although I will be honest that this table did get sacrificed to the epoxy gods quite a while ago. I'm also hoping that I can just kind of push against the table and I don't have to strap the table down to something as I'm pulling on the torque wrench, but we'll see. To start with, I'm just using a chisel jammed into that slot in the sun gear to hold it, and then putting it against the casing bolts into the vise to basically lock it all out. And then I'll be using the bolts on the hub and hopefully gripping it with a hex socket. Hopefully being the key word. We're starting off at 40 Newton meters. I won't be showing you much of this torque wrench detail because frankly you can't see anything on the camera. So I'm afraid you'll just have to trust me on that. I did, however, become quite immediately aware that this socket idea wasn't quite going to work for the higher numbers, but it did at least allow me to click off at 40 Newton meters. However, when I moved up to 60 Newton meters, it just kept slipping on the bolts. And I did try to jam different things in, as you can see here, and it still didn't work.
Well, this is now impossible.
So I had to go to the old Mark IV prototype and take off a piece of the exoskeleton to use as something to grip. However, to be honest, at this point I was starting to think, is this going to be a complete disaster, full stop? So I decided to just get this bar out and see if it'll actually take just putting some leverage on it, which thankfully it did. But I was doing that thinking, wow, that's flexed a lot. And it turns out this is why, because it just bent all the bolts instead. So I did just have to rebolt all of that, try get it all tighter down and neater. And then I decided to cut a 3/4 square hole into the carbon fibre plate, just so I can actually attach the torque wrench directly to that. But then the next problem I found was that jamming the chisel into the sun gear didn't quite work, so I then had to take it apart again and make a little square keyway out of some threaded bar that I had, insert that into the sun gear, and then I had to break the CNC out again and make an aluminium plate with a square cut out in the centre so it could all be locked together. And then on take 54, something finally broke, but not the gear teeth. Instead, it was the 3D printed planetary gear carrier. This just sheared off from the hub, so to solve this issue, I then went into my actuator spares box and pulled out some pieces from an old prototype. This being an old planetary gear carrier that was aluminium and steel, so I got the carbon gears and everything and got it all built back up. Confident that these pieces, while less neat, will at least hold up to the test. And at long last, I was finally able to reach 60 Newton meters. However, I could already see that it was starting to bend and twist the carbon fibre, particularly around where I've had to cut that square out for the torque wrench to go in. But I was able to kind of brace myself, brace the torque wrench, flatten everything, and still get 80 Newton meters out of it next. Unfortunately, a lot more problems started to arise at 100 Newton meters. One of which being the quarter drive fitting was basically turning inside the carbon fibre, so I had to try secure it with some mole grips and cable ties, as you can see. And there's me hoping to have actually cracked a tooth off at this point, but no. Turns out instead what was happening was the sun gear was basically cockling inside. Even with the back plate and square peg. This technically is a failure, of course, but it's not the kind of failure that I was wanting, as it's basically a failure of the whole actuator not being complete. So I went back to the actuator parts bin and managed to find one of the old steel sun gears, which I jammed the teeth together using some bolts and tried again. And I really thought I'd done it that time, only to find when I took it apart, it actually just managed to roll over the bolts. I think the entire casing just flexed a bit. It rolled over all the bolts that were jamming it together, and I couldn't actually see any particular damage on any of the teeth. So I decided to try even more bolts and jam it in just to see if I can get some gear teeth to break. And it did the same thing again, where it just kind of ran over them, and then when I took it all apart, I couldn't actually find any in particular damage to any of the teeth, which is odd because it really sounds like they should be in pieces. But there was barely a mark, so the last thing I could actually think of doing was just drilling straight through the planetary gear carrier, straight through the gears, just to try and make the only failure point possible, the actual gear teeth. And here is where I came up a failure that I can't quite get round at the minute, and that is the exoskeleton piece that I'm using. It's basically just twisting out of place completely where I've got the torque wrench into it. I tried to secure it with putting some bolts into the arm and then tying the mole grips to it to try and hold it all in place, but I just couldn't quite do it. But this has actually led me on to a final conclusion.
And that conclusion is that while I haven't been able to test these gears to destruction like I wanted for this video, I have become fairly certain that the weak point in these actuators in the future will not be those gear teeth. So number one, you've got the brushless motor on the back, and the most likely thing with this is you'll just get basically slip in the brushless motor before I actually reach a point where it might damage these gear teeth under torque. But even if somehow that wasn't the case and it became mechanically locked in whatever way, due to the requirement of making this actuator as narrow as possible, the internals for this, say the internal walls or the planetary gear carrier itself, are always going to be quite thin in bracket thickness. So the carrier is always going to be probably 2 or 3 millimeters wide, which I will be making out of carbon fibre in the future. The faces on the front and back are going to be the same. Again, I'll make the faces out of carbon fibre. However, there will be internal parts, internal walls essentially, that are probably going to be PETG carbon fibre filament, just because it makes more sense being able to have something where the bearing race sits fully into it, while having walls that basically go thin to allow for more room inside for either bolt heads or for coupled enamel wire on the brushless motor side. Meaning that these parts are most likely going to be the weak point in the actuator instead of the gears. And what will probably happen in a case of damage, or basically having them over torqued, is that all those pieces will bend and then basically cockle the gears over in that way. So the gears won't actually break, but the gearbox might essentially cease functioning that way, while the teeth will remain intact. However, in the future, I still want to test these teeth to destruction, but I'm going to have to make like a full steel rig that bolts into a vise properly with a correct socket fitting on it. At which point, what torque setting do I think I'll get up to? I think I'll certainly make 120 newton meters, but to be honest, if it's all nicely machined and tight and everything like that, and I've got a good holder on it, I actually think it's going to do quite a lot more. At no point in this did I see a potential failure on the actual gear teeth. So I think I'm probably going to get up to probably 200 newton meters, somewhere around that mark, maybe a bit more, maybe a bit less. Which, if I get up to that amount, that will certainly be good enough for this exoskeleton. I'm also going to modify my design for the planetary gears. This is just one of the early designs of gearboxes that I did a while ago. But it's the one that I've used because I've known if I've printed it out or had it made out of laser cut steel, it's always worked and always meshed fairly well. But in the future, I certainly want to get it neater. And I want to try different gearbox ratios. I don't know how small I'll be able to get those gearbox ratios, as this gearbox is 6:1. I don't know if I'll get to 9:1 with realistic end mill sizes that I can use. Also, something to note, some of you are probably thinking, aren't steel gears better anyway? And the answer is probably yes. And I may still do them in the future. However, this I think is an excellent method for basically doing the next prototype. So when I get it all up and running, if I then want to make steel gearboxes after that, and I know exactly the design to use, and I'm just getting multiples of like 10 of them, then I might get steel gearboxes, and that should be easier to actually get someone to cut the pieces for me. So what's next in the project? Suit-wise, it'll probably be the back pieces for the next exoskeleton. I'll be coming back to this actuator in the future, but I still need to learn some new stuff and get some pieces made and cut out. I've also got some other things like a custom sledgehammer on the way. So once again, if you would like to see that, please like and subscribe. Thank you for watching, and I hope you have a great week.